The next speaker is Professor Karthik Duraisamy from the University of Michigan, and he's going to talk about truly, underlined, predictive reduced order modeling for complex multi-scale problems. Over to you.
Thank you very much. So I put truly in the title and underlined it just to be a little bit provocative, right? And also to make a point that sometimes we need to be much more careful about how to quantify what the goal of what we are doing. And also I want to spur some discussion. If it is criticism, I really welcome it. That's what I'm looking for. So let's get started. So of course, a lot of work went into this, done by a lot of people, but I want to call out three particular members of my team. I mean, I should say former members, because Cheng is an assistant professor now, and Chris and Nick are at National Labs. So these three folks did a lot of the work that I'm going to talk about, but the larger team. So I direct the Center of Excellence for the Air Force at University of Michigan. It's in its 6th year. And in some sense, most of what I'm showing is a culmination of the work of the entire team. So I want to mention that. All right, so one of the main motivations of today's talk is, of course, there is complex simulations and there are complex simulations, right? So things that I'm interested in, for instance, currently is if you have something like a rocket combustor and we are doing high fidelity simulations, there is flow, there is acoustics, there is hydrodynamics, chemical reaction. There is a lot that is happening. And these are not linear by any means. The pressure fluctuations themselves have many bars. So these are hard calculations. And doing a calculation like this for one of these injectors is about, for 50 milliseconds of real world time, is already a large calculation. And a real rocket combustor has hundreds of these, right? So we need to reduce the complexity in one way or the other. So, and you can reduce complexity in many ways. I'm focusing on the reduced order way of doing things, which is try to retain the physical fidelity, but do a mathematical order reduction. I'll get into the details. And so here you, at least theoretically speaking, you maintain the mathematical and physical consistency, but then can you ensure robustness and generalization, right? So that's a question. There's the other way, traditionally we've always done, which is physical complexity reduction. So here you look at the equations and then you talk about, okay, what this term may not be important, or you can make this assumption. So this obviously, you get a lot more insight and potentially much more efficiency. But then every assumption you make maybe is justified in an intuitive sense, but quantitatively you lose things that you may not be able to quantify, right? So I'm going to speak more about reduced order, almost exclusively about the reduced order models today. I'll just mention reduced fidelity in maybe a couple of slides from now as one way of what I mean by truly predictive. Okay. Actually, this is the slide, and after this, I'm not talking about reduced fidelity models, right? So I call this to be a predictive modeling goal, where say you have data from some shock turbulence interaction, you have data from wind tunnels where it's extremely sparse, and then you have some data from some larger dissimulation, and then you build some model forms into, say, a PDE, and then you use that model form to predict systems that are yet to be designed, right? So these are completely different systems from which, compared to the data that we originally got. So right. So I would call this a true prediction, in the sense that in the physical space, you're actually looking at phenomena that maybe you saw the phenomena in some respect. The phenomena was embedded in the data, but then the geometry and other configurational details were not. So I would call this to be a truly predictive calculation. So in the current context, mainly the goal of today's talk Again, going back to something like a rocket combustor, I said there are many hundreds of injectors in there. So the goal here is not just to reproduce what I saw offline, right? So you have, a nice simulation that you ran offline, and then you learn something from it, and then you reproduce the offline dynamics. Of course, that has some uses, but that's not what I call as truly predictive modeling in the current context, right? It is also not reproducing what we saw offline. That's a subset. And I also do not call interpolation, like maybe you observe data in one part of parameter space, maybe you observe data in another part of parameter space, and then you're interpolating. It has a lot of uses, but I would call that interpolation. I would not call that predictive modeling, truly predictive modeling. So what we want to do here is do future state prediction, where you observe maybe the dynamics of the system for a limited time interval, and you want to predict the future, not just for a short amount of time, but well beyond the training horizon. And certainly we're not restricted to time periodic systems. I would call that to be a true prediction. I would also call parametric prediction outside the parameter range. Okay, so this is not, you're not interpolating between a few points. That again, that is hard enough, and it's useful in some cases, but that's not what I call as truly predictive modeling. And one other thing that I want to show today is, can you build reduced order models of components of a system, and then you assemble each of those components to form a full system, right? So that is also what I would call as truly predictive modeling. And we want to do all of these things in very hard problems, right? The kind of problem that I showed here. We're not doing this in a toy problem by any means. We want to take all of these techniques and then apply them to these very complex problems and see if we can do something useful, right? And one of the things I'm avoiding today on purpose is using neural networks, not because I have any particular hatred for them, but so I've been playing with neural networks in various forms for almost 12 years now. Maybe that's half the time Petros has been playing with neural networks. But again, they have strengths, weaknesses. They may not be as reliable as we want them to be. We can go into a discussion on why I avoid this neural network part, maybe tomorrow or any of those panels. There are very many things they do well, but not the kind of things that I was talking about today. So one thing, and I said I've been playing with data-driven modeling for more than a decade now, and one thing that I do place a lot of faith on is power of linear methods of various types, right? So it's not just linearizing the system about a point and then trying to be predictive, but there is a lot that we can use with linear mechanisms. And here is a very, very simple example. So here, this is just a Van der Pol oscillator, and maybe it's not very visible, but I'm learning from data from this region, and then I'm able to predict for the whole region. Okay, so it's not a complex task, and in fact, if you read our paper, we'll show why we are able to be predictive, and you can actually quantitatively say how many time delays you need. Even though the dynamics is nonlinear, you can use a linear embedding, and just the time delays is gonna get you the whole dynamics. But and in that paper, we also show how many you need. We derive a criteria for that for scalar and vector systems. And to a certain degree, these kind of techniques can be used even for slightly more complex problems like Rayleigh-Bernard. Of course, you need more delays, and conditioning is an issue, but you can sort of slowly get there. And you can also extend this to say a Koopman context and get a little more. Okay, but I'm trying to avoid any type of neural networks because again all of this work that I'm going to show today is a culmination of 6 years of work as part of a large center with many universities, a lot of researchers, and over a period of time we invested a lot in neural networks, but then a particular class of methods helped us achieve our goals. I'm going to talk about them. Anyway, this is probably towards the end. So I'm going to focus mainly on linear manifold reduced order models with a twist. So if you take your trial basis to be linear, like you use a standard POD, it simplifies the math a lot. But then if you keep the basis static, then you're going to lose predictivity, right? So we're going to use adaptive linear manifolds to achieve all of the predictive goals that I mentioned earlier on complex problems. So earlier this year, we had a tutorial session on reduced order modeling. So I'm not going to go through all of the basics here, but I'll just give you a quick snapshot, and then I'm going to show you, direct you to the resources. So I created a 50-60 page document that covers the basics, and the slides are available, and the video is also available from the tutorial earlier in the year. The idea is fairly simple, right? So let's say this is your dynamical system that's very complex, right? Think about the rocket combustor, this semi-discrete version of the rocket combustor. So here the dimension of F would be 1 billion, corresponding to every spatial point and number of degrees of freedom at every point. You can write that as a discrete full order model, which is basically your favorite time marching method. And the starting point is you can take your unknown solution and you can write it as an expansion in a trial basis B. Okay, so this you take k of these trial basis functions. The QR are your basis modes. So the goal is you want to take this system of dimension n and reduce it to a system of dimension k, and k would be, you're going from 1 billion to 100, right? So that's the goal here. And again, the simplest way to do it is the Galerkin projection. It's very simple. The trial base and the test bases are the same. So you're going to take this expansion, which I just spoke about. You're going to substitute that in this equation. And then you're going to basically multiply that system by B transpose, because the test basis is the same as the trial basis, and you get this simple system of equations. So now you have the system of equations for the basis coefficients R, and this is of dimension k, right, instead of n. But of course, there is complexity here. You need to use something called hyperreduction to further reduce the complexity, but that's the high-level idea. And there are two ways of proceeding that are most common. So one is the Galerkin projection, which I just spoke about. It tends to work very well when you have elliptic problems. But then if you have you have different types of physics, say hyperbolic, non-elliptic of any type, you would need stabilization. And one way to approach stabilization is the least squares projection. So this is effectively a Petrov-Galerkin projection with where the test basis depends on the trial basis and the evolving solution. Okay. And so reduced order models have been used, I think, for at least 5 decades, as far as I know. And they've seen a lot of resurgence in interest over the past decade or so. And there is a company called Axelos, which I think many of you may know. So they do very good work where they can take a ship structure and break them down into simple components and very quickly build a reduced order model that's orders of magnitude more efficient. The challenge is many of these commercially successful reduced order models are applied to mostly linear or mildly nonlinear problems, or elliptic problems, highly viscous problems. Nothing wrong with that. They're still very useful, just not for our type of applications. And again, there's been a lot of work that, coming into where we started 6-7 years ago, we built on a lot of work. I've listed a few things. I covered some of these things in the tutorial, so I'm not going to go into detail. I'll just point to the resources that are available. If you go to actually my tutorial from earlier in the year in the Newton Institute, there are slides and notes and actually even software that you can play with. But the thing that I want to mention is when we apply these reduced order models to the kind of complexity that I showed earlier, a lot of things that are available break down. And so today's talk, I'm going to focus on three things. One is how to stabilize these reduced order models. Second is how to make them predictive in the sense that I described earlier. And then how do you network these reduced order models together to get emergent dynamics? Okay. And I already spoke about the physics. What I'm going to talk about is not particular to this physics, but this is some of the motivating applications. As I mentioned earlier, there is flow, reaction, acoustics. The other thing to mention is the stiffness of this system is extremely high. Condition numbers run into order of 10 to the 12. And it's also very dispersed features. And the flows are necessarily chaotic, so nothing gets repeated. So that's another challenge. Okay, all right. So how do we go about it, right? So three things that I want to talk about. Let's see how I'm doing on time. I think we'll stop it. I'm about 15 minutes in. All right. The first thing is, how do you keep these reduced order models really stable, right, to even give an answer? And the second one is predictivity, and the third one is how do you use these reduced order models to solve problems that are not tractable otherwise? Okay, so I mentioned to you earlier that you can use different techniques to stabilize reduced order models, and one of them is the least squares projection. So we, using some experience from running hard CFD calculations, we learned some lessons and then we applied it to the reduced order model, right? The idea is, okay, again, you start from your full order model equations here. So then we said, okay, instead of building a basis for the state variables, how about we transform the state variables to a different set of complete variables? Okay, so you're going from Q to some S. Okay, so and this S may be more convenient variables, right? You can think about S to be primitive variables, characteristic variables. You can think of S to be entropy variables. And as soon as you bring in entropy variables, you can think about bringing in some additional stability that you didn't have if you're building reduced order models for the original system. So nevertheless, you make that substitution. So these are your equations in your transform variables. I've also introduced a pseudo time step. Okay, so because within each physical time step, you can do zero time stepping. And you can then apply a Newton type iteration within each time step to get what I call as a fully discrete residual. And then we introduce a linear decomposition for this set of equations for the variable S. Okay, so S tilde is the projected version of S. The scaling matrix is very important here. And then we say, okay, now we take these discrete residual equations, and then we substitute this expansion into this discrete residual equations, and then we minimize the least squares residual with another scaling. Okay, so these are a bunch of steps. These are all simple, right? All of these have been done in some context before, but after almost 3 years of struggling to keep ROM stable, we arrived at this method. Not in logical progression, but got there. So anyway, so the number of things that are useful here is the transform variables makes it easier to enforce conservation. And so this least squares problem can also be augmented with constraints that make it conservative. And it's also discretely consistent, which means at every zero time step, you're effectively computing a new test basis. Okay. So again, as people who do ROMs know, it's not just enough to get the reduced equations. You need to sample them appropriately to get efficiency. So that process is called hyperreduction. Again, it's in the tutorial material. So this part I'm going to skip because the next two things are the ones that I want to focus on, but I'm doing this for completeness. But at the end of the day, going from your capital N, which could be in the billions, you end up going to a system with a number of operations scaling with NS. NS is the number of samples. Okay? And this could be, again, say 1,000. And if we are careful about how we do the sampling and careful about how we do the parallelization, we can get up to about 4 orders of magnitude saving in computational time with this approach, with very minimal error. I'll be more quantitative as I move on. But again, none of what I'm showing is what I would call as truly predictive yet. Okay, so but we're thrilled to get these results a few years ago after, Yeah, that reduction was achieved in 2 ways, right? So no, this gamma, so this transformation does not do any dimension reduction. Yeah, yes. So this is the one that gives you dimension reduction. So S would be, say, 1 billion, and SR would be 100. So that's the main dimension reduction so far. Oh, V, to start with, it could be just be a POD. You can take snapshots of the solution and then compute a POD basis to start with. Yes, so far, yes. Yeah, I'm going to improve on it as we move on, right? Clearly, if you project dynamics so complex to a linear manifold, things are not going to work if you want to be truly predictive, right? So here are some results, at least, to show that these things get us to the ballpark. So this is a 3-dimensional rocket combustor, less complex than the one that I showed in the beginning, because we want to run many experiments and convince ourselves that these things work. This is the kind of, if you do an SVD and you look at the singular value, this is the kind of decay you have. So with about 100 modes, you can get to within 99.9% accuracy, at least to reconstruct what you've seen before. And these things do okay these things do well in reconstruction. Maybe they do reasonably okay in prediction. But the nice thing is you can go all the way down to 20 modes and you can get pretty good cost reduction. You lose some accuracy, but then you get close. Okay. But again, the challenge is when you go out of the training snapshots, right? So you take snapshots during training, you construct your basis V, and then you let these ROMs go. They do pretty well. This is, some measure of the errors. Just think of this as, say, 0.01 could be like maybe 1% error, maybe. But then you can clearly see that when you go out of the training region, you're going to lose some predictive capabilities. And then if something changes in the boundary condition, then this thing would completely collapse, right? But this beginning is needed at least to make sure you can get answers, right? Some results. So, okay, how do we get past this? So we invested very heavily about 3-4 years ago into going to nonlinear manifolds. The same projection step that I mentioned earlier, I can still use the same transformation to be okay. And then instead of using a linear basis, right, I could go to a neural network, right? Pretty much an autoencoder that Luca was talking about earlier. So this, you go from S to SR, your reduced variables, which would be the latent space of your autoencoder. And you can try to get results. So what we ended up seeing was the 1 or 2 times we got lucky, and that's almost like what Luca was saying. But mostly, these things had no inherent predictive capability if you moved out of training. These were amazing to compress data that it had seen before, and the more data you threw in, they got better and better. But then if you get out of training, these things can fail very spectacularly, right? Nothing as gentle as what you saw with these linear manifold models. That's not to say that nobody can design a neural network to make this work, but we did invest about 5 or 6 PhD student years into this at a minimum. Okay.
Because there is no such nonlinear mapping.
Yeah, I mean, yeah, even what Luca was able to get, we could not get about 3 years ago. Take a minimal flow unit and we could do an autoencoder. We threw a lot of data, but yet there was no representation that we could, get away with. The other thing is, you cannot have a latent variable dimension of 1000 and then project the equations. That also becomes extremely expensive. It's okay if you replace the entire flow by a neural network, but finding that latent space is one thing, and the second thing is if it goes slightly out of the manifold, then it fails spectacularly, right? There is just no predictable way it can go. Okay, all right. So how do we get away from the problem? The main thing that I want you to take away is adaptivity, right? So linear manifolds may be perfectly okay as long as you track the solution. Okay? So, and this is very easy to see. You can take this extremely simple case. You just think of a pulse that is moving from left to right. And if you construct a flow field snapshots and you assemble them in a matrix to do SVD, this is going to look like a diagonal matrix, and you cannot reduce a diagonal matrix, right? So that's if you go linear. If you go nonlinear manifolds with neural networks, especially these kind of problems, you can do very well, right? It can learn the underlying structure, it can learn how to handle these things. So for very simple problems, I think nonlinear manifolds can help break the Kolmogorov barrier easily. So the approach we follow is, as I mentioned, it's an adaptive basis approach. So I don't know, again, these lines are somewhat misaligned, but anyway, let's say your true dynamics was 3-dimensional, as in this spiral here, and you want to build a 1-dimensional manifold, linear manifold. The best you can do is this, right? So this would be your basis if you want to, L2 norm best fit for the dynamics, right? And this won't be of any use for anyone. So what we end up doing here is, at this time, we build a linear manifold that is tangent, right? At a later time, we build a linear manifold that's tangent here. At a later time, we build a linear manifold that's tangent here. And for all of these things, we project the dynamics onto that locally linear manifold. That's the high-level idea. We'll get into details. So again, showing the reduced order model earlier, the reduced order model with a static basis, right? So V is your trial basis, W is your test basis, and they were both fixed. Right? Actually, if you use the least squares Galerkin projection, the W changes in time, but V doesn't. The ROM with adaptive basis, everything becomes a function of time, so it can be much more efficient. And this is, we didn't come up with adaptive basis. Ben Perstoffer was also part of our group. So we started with some of what he had done and we added our additions to it. Okay, so let's look at the dynamic. Okay, so let's take a very simple linear system, right? This is your, let's consider this the full order model. And you can do an exact decomposition of this state variable Q. So this is your POD basis expansion, and this is the residual. Now you can substitute this equation into this decomposition into this full order model, and you can track the exact evolution. And you can actually write the exact evolution in terms of the reduced variable. Okay, so if you were to get an exact evolution of exact reduced order model of your full order model equations, this is how it would look like. But of course, this involves the space that you left out. So you won't be saving any complexity here, but this is how the exact dynamics evolves. But if you do your standard reduced order model like Galerkin or least squares Petrov-Galerkin, you end up with this type of an approximation. So the exact evolution is supposed to look like this. Your evolution looks like this, so there is a difference. So our idea is, okay, so this is the exact evolution. And my approximation was in the previous time step, I had a basis V. So I'm going to augment the basis at every time step by adding a delta to the basis, okay? So at every time step, I'm going to somehow compute a delta. And the reason why I need this really is the inadequacy of the basis effectively generates subscales that don't belong in that manifold. So I'm trying to basically rotate the basis to correct for what I missed out, okay? And you can actually, it's a simple solution, you can solve it analytically. But of course, this is not the whole story, because this is assuming we have access to this Q, which we don't. So the actual algorithm is somewhat complex, but I will walk you through it. That's why it's a deep dive, and we can always discuss more details later. So after all the bells and whistles are added to the least squares based variable transformation method that I showed earlier, this is how the reduced order model looks like. So V is your trial basis. This would be your test basis. S would be the points at which you sample, etc. So what we end up doing is we would estimate the state at the sampled points, and we'll compute the full state information at the sampled points. And every few time steps, we also estimate the state at the points that are not sampled. So we have an estimate. So then what we end up doing is, let's look at this equation. The basis at every time step is the old basis plus a correction. Again, and these S are basically sample matrices, and S star is outside the sample matrices. So you can basically, it's an exact solution to an optimization problem. The way you think about it is,
How do you decide the sampling points and the ones that are not sampled?
Yeah, so we initially used a method based on the QR decomposition. It basically, you take the basis functions, and then you do a QR decomposition of the basis functions, and then it's going to rank. It's a pivoted QR. It's basically going to rank which are the most important points. There are more fancy techniques based on eigenvector sampling. It's all based on linear projections, right? But what we end up doing, what we found is, ultimately, you can take the full order snapshots. See, this is the problem you're effectively solving. You're taking the full order snapshots. You are getting the projected version of the full order snapshots, and then you want to find the set of sampling points that minimizes that residual, right? So this is the exact problem statement. And there are multiple ways of simplifying this, because this can become hard, but that's the idea. You have your full snapshot, you have your reconstructed snapshot, and you find this, you solve an optimization problem to find this.
Then your computation works.
Actually, we use tricks to approximate that, so we can get it almost explicitly, order n cost, order ns cost.
You don't need patient.
You don't, no, if you want to solve that problem exactly, then you need a lot of machinery, but we don't solve that exactly. And we find that you don't need to, because end of the day, we find whatever nice method we use to find the sampling points, it's still not perfect. So we end up oversampling randomly anyway on top of what we have. But if you're doing it precisely, you would solve this optimization problem. Sure, yeah, that's an issue, but yeah, that's certainly one of the issues. I mean, if you look at my last slide and I say, what is the biggest uncertainty? I would say finding the sampling points efficiently and updating them is the one place where we need more research. But yes, the questions you ask are certainly valid. Again, like I said, whatever we do in the end, there are 3 or 4 classes of methods that we use to find sampling points. And even if we end up solving that optimization problem exactly, you still need oversampling, because think of a domain with 1 billion points, and you want, say, 100 or 1,000, right? That is not going to cut it. So we get these sampling points, and then we have some other more ad hoc ways of describing it. But it is certainly an open question, how to do this efficiently in the context of adaptive basis is an open problem. In the context of static basis methods, I would say things are much more mature. There's some very good techniques that are out there. But for adaptive, that's certainly an open question. And it's in my last slide. So again, you can do computational complexity analysis. It has a lot of details, but I'll just say that we've done that and we've verified that analysis is valid, and just leave it there. Let's get to results, because now this exposes some interesting aspects of what I spoke about, and also I was provocative in the beginning, so this is now I get to pay my dues a bit. So this is not, I mean, I'm going to show more complex problems, but this problem has enough complexity to speak to some of the challenges I mentioned earlier, right? Just two shear layers at different temperatures and different speeds, slip wall top and bottom, and you put a pressure probe somewhere, you're going to get this type of behavior. We can argue the dimension of the space, etc., but it's hard to work with this. So here is a challenge with, say, a POD basis, and we saw the same issues even with any autoencoder we ended up using. Maybe Luca's autoencoder or others may work better. It is something that we want to try. So here you take 0.167 milliseconds of training data. Okay, so this corresponds to one acoustic cycle corresponding to this flow problem. And you take flow snapshots and you put them in a matrix, do an SVD, and you look and you say, how many modes do I need to capture 99.99% of the energy? It says 20 modes. Okay, so that sounds like a good idea. But then you extend the range of your training snapshots, and to get the same amount of energy, it says you need 60 modes. And then you extend your training interval, looks like you need 120 modes to get the same, right? It keeps going. So it's basically an infinite dimensional. You basically need infinite dimensions to characterize this, because after the initial transient, every time snapshot is different from the other. Okay, so how many ever basis modes you use, you're never going to capture what is important, especially if you want to be predictive. So sure enough, so here I have a bunch of curves. I apologize, but the black is the full order model, and the blue is a static basis reduced sum model trained on a long time period. The green is a static basis reduced sum model trained on a smaller time period. And they just, as soon as they get outside the training window, they stop being predictive. Whereas the adaptive basis, which was initially trained on just this region, captures the full dynamics very well, even if you assume it to be pointwise. And now so this is future state prediction, well beyond the initial training time, so that's good.
Is it different longer time period or spatial period?
It's the same spatial period, but over a longer time period. Yeah. So now we do something interesting. Now we say, okay, take the same model that was trained earlier, and you reduce the speed on the top from 100 meter per second to 50 meter per second. So clearly some new unseen dynamics happen, which the adaptive basis gets, right? So this is the full order model and the adaptive basis reduced order model. Whereas the static basis one, whether we use linear or nonlinear manifolds, they never really, I mean, they think their dynamics live somewhere, right? They're doing something completely different. In the adaptive, in this case, we are probably doing it, actually in this case, we're doing every time step. So, yeah, so there is a cost, okay? But even though we are training even though we are finding the adaptive basis every time step, that is still order of roughly k complexity, right? You're not It's not order n complexity. It is still order k complexity.
But don't you need the full thing?
So you don't need the full thing. So if you look at this algorithm, so the state estimate has to be at the sampled points. Okay. Now there is another bottleneck. So there is another hyperparameter in this problem. You are correct. So every ZS time steps. Okay. So this ZS could be 25 or it could be 50 or whatever. So at every ZS time steps, for all practical purposes, we are actually solving the full system. So you're correct. So every, say, 50 time steps, we are also like looking for an estimate of the solution at the unsampled points as well. So that would be the bottleneck, and that's what I was showing here. So you're ultimately limited by ZS, but then to find the solution at those points, you can actually be less accurate than finding the solution at the sampling points. So what you end up, I mean, you get this amazing predictivity, but what you end up paying for is where you were headed with, which is earlier with the static basis reduced model, I showed 4 orders of magnitude reduction in computational cost, whereas here I'm between 1 and 2 orders of magnitude because of this bottleneck, right? So if I can increase ZS to be much more, and I think here something like neural networks or a quadratic manifold can help, because if I, instead of adaptive linear, if I go adaptive nonlinear, maybe I do not need to say look at state estimates every 50 or so time steps, but then they can fail for other reasons, right? And reducing the cost is hard. Again, the next example is increasing the speed. Okay, so now let's go to a harder problem. This is what we are most proud of after 5 years of work. So here is that rocket combustor that I showed earlier. So here we take things even more extreme. So here the training is only in this region. Okay, so it's literally almost negligible training. So here is where we construct the initial snapshots. We do a POD, and then the adaptive basis gets updated. So this is the full order model. This is the reduced order model. And what did I want to say here? Yes, the reduced order model is actually of dimension 5. Okay, so you're going from, in this case, you're going from 500,000 to 5. And you're using about 0.5% of the sampling points, right? So earlier, but you still need to sample the state at some point, so that number is 0.5 here. So again, here, this is the offline training and this is the prediction. And this figure shows how the sampling points, are adapted with time. So again, now we do something like the other test. So now we change the oxidizer from 100% to 50%. Okay, so the flow topology completely changes. And the same reduced order model that I showed earlier, trained on the previous snapshot, is able to get the dynamics. Of course, after some time, there is some departure. Perhaps we need to reduce ZS, or we can use other mechanisms if we are not happy with it. But statistics are well replicated. Same thing with increased mass instead of reduced mass, and it still does very well. And as you can see, the dynamics is okay. So these things are out of sync. But anyway, so but again, it's one thing to show a picture on these problems. It's also another to have this in a production code, doing everything in a massively parallel setting. But one of my students spent about 2 years just coding up the load balancing for this, because if you have a situation like this and sampling points are moving all around and you're running this on a parallel computer, every time you adapt your sampling points, you also have to do a redistribution of the load. Okay, so this is a scaling bottleneck, and this we thought was pretty much impossible to do it efficiently. But again, like I said, 24 months later, Nick, in the 7th year of his PhD, was able to do it. But he's a computational physicist at Lawrence Livermore the day after he defended his thesis. So it worked out for him. But it is possible to do it, but a lot of under the hood things. So I don't want to give you the impression that somehow these algorithms are ready and you can just apply them. There is a lot of work behind the scenes that needs to happen. Okay, so message from that is adaptive basis can really make your arms powerful with a lot of pain. All right, the last part is tractability. And I mentioned earlier, right, if the flow field corresponding to one injector takes a month to simulate on a university scale cluster, how can we address a real rocket combustor that has hundreds of injectors, right? So this is an exascale problem even to run one full auto model. So what we want to do is, again, being able to, at least this is what we promised the Air Force that we will do by end of year 6. I had no faith in that when I wrote the proposal. And I told the program manager that I had no faith that we would end up there. And he said, be aspirational. And somehow it all kind of worked out. So how you want to develop these reduced order models for components, and then you want to assemble them to see how engines with different configurations look like. So what we end up doing is we take a injector flow field, single injector, and then we perturb it in all kinds of possible ways and build a reduced order model. And then we stitch those reduced order models together to form a rocket engine, right? So think about this rocket engine having 3 injectors. So this is the physics intensive part of the field. So here you just have pretty much acoustics. So you don't need to reduce complexity here. Here is where all the reactions and other things happen. So you can have a 5 injector combustor. You can have a 7 injector combustor. You can have a combustor with a different geometry. So all of these are possible. So here is how it happens in practice. There is some details about how you force it. Maybe it's not too interesting for you at this point, but bottom line is we take single injector domains and we train them. And again, we come from the CFD world. So how do you interface to reduced order models that are next to each other? I mean, I was brought up in finite volumes like many of us. We just use a simple row flux exchange between 2 interfaces. Yeah, sure. Yeah.
They are not aware of omega.
They are not aware of omega f at all, but we give some random set of forcing, this external boundary, just to have them see that. But they are not. I'm going to show you a truly emergent thing, and you can take me to task there if I'm not.
These are all unsteady things. Steady state.
Oh, there is no steady state here. These are all chaotic, unsteady.
And how do you match time space between the different reduced order models?
There is no. I mean, all of these are the same. I mean, which different reduced order
In
models?
the previous picture, if I understood well,
Yeah.
is this a spatial decomposition?
Yeah, it's a spatial decomposition.
And then all the times are synchronized for all the reduced order models?
So there is only one reduced order model that's developed, but it is still solving it's still projecting the Navier-Stokes, so that it's still projecting to those equations, right? So that's automatically insane. So all these reduced order models talk to each other. So this is a reduced order model. This is another reduced order model. So at the interface, you're basically computing the row flux to get the flux to cross the interface. See, remember, each reduced order model is still solving the Navier-Stokes equations in a lower dimensional manifold, right? So, and they talk to each other via a simple flux exchange. So they are synchronized because of the flux exchange on the interfaces. Okay, so here we take that single injector ROM and we replicate it, and I'm comparing it against the full order model. Like one of the curves is the full order model. This is the DFD spectrum. That's what I'm comparing against. Of course, it's not like spot on, but it's capturing all the important dynamics well. Now we go to 5 injectors, and again, it's doing a pretty reasonable job. go to 7 injectors, this is very cool because you didn't see this in the 3 and 5 injectors. When you go to 7 injectors, there is a huge transverse instability, and that is also picked up by the reduced order model, especially in the pressure. Again, it's not perfect, but it is. I call this emergence because, first of all, ROMs were trained on something, but of course they're adapting. And in the 3 and 5, you couldn't see that huge transverse instability. They're mostly longitudinal, but when you go to 7, there's a huge sideways instability that emerges, and the ROMs are able to pick up. Okay, so again, what are the 3 things I showed? So extreme stiffness, nonlinearity, multi-scale nature poses robustness challenges. So that was basically the first 3 years of work for us to get an answer. And then we found, okay, whatever we do, even if it's a nonlinear manifold, if you have chaotic dynamics, especially dynamics that is as stiff and dispersed, right? So as what I showed, you cannot use static basis. And we also wanted to address ROMs of systems for which the full order model may be inaffordable. So that was the component ROM part. So what did we end up doing? So to keep the ROM stable, there was a transformation to a secondary variables. Then we scaled it. That scaling was important. Then we dual time step, then we scale again. And then we apply the least squares transformation. So that gives us a discretely symmetric price consistent, well-conditioned ROM. And then the adaptive basis helped us break the Kolmogorov N-width. So did the nonlinear manifolds. The adaptive basis reduces projection error. So did the nonlinear manifold. But then the nonlinear manifolds, I didn't show the nonlinear autoencoders in this, but they were just not useful in the end if we went out of the prediction domain. And yeah, the last thing is you take this truncated domain training and then you give them some kind of perturbations. And then you integrate these ROMs as a network. You make them talk at the interfaces. You can do full order simulations. And Petros, to your point, so these things do break once in a while. And mainly they break because the sampling goes off. That's enough. This is the biggest, I think, open area of research for us to work for, get those sampling points, both for adaptive ROMs, but also for the nonlinear manifolds. And the other set of topics that I didn't speak about today, but some of the members in our team, especially Karen Wilcox's group, so they've done non-intrusive ROMs where they skip the Gaussian equations. And what was surprising in their results was when you talk about static manifolds, and I used to bet that non-intrusive ROMs can never beat intrusive reduced order models because we have this notion that we have the physics, we have the equations. But Karen's non-intrusive ROMs beat our intrusive ROMs any day, and they were about 1 million times faster for static manifolds. Of course, for non-intrusive ROMs, you cannot have the same kind of adaptivity because I use the Gaussian equations to do the adaptivity. So for static basis, I think there is not too much of a point in doing intrusive reduced order models based on some of the work that's coming out of Karen's group, and there's also people doing quadratic manifolds. But if you want adaptivity, which is the key to the true prediction that I spoke earlier, I think having the equations is a good thing. This is all the work that's happening in the center. I spoke about these 3 things. There's a lot of other things happening as well. So you can find all of that on our website. And again, I should thank the Air Force for funding us for 6 years. They renewed us 3 times, and it looks like they may renew us again beyond 6 years. So things are going well, and without their patience, this would not have been possible. Because first 3 years, every conference, every review meeting, we show up with terrible results. And then slowly, one thing after the other started working, and I spoke about some aspects of this. All right, so I will stop here and welcome criticism and comments. Honestly, give me some trouble. No?
Well, I have a general
Yeah.
question about anti-epileptic tactics.
Yeah.
What you call emergent behavior
Yeah.
for the large scale
Yeah.
is really a sort of a large scale modulation that comes from interaction.
Yeah, sure.
Not a small scale.
Yeah, it's not emergence from the small.
Right.
It's more like interactive.
It's interaction, right? So, and you know, you and I have been spending a lot of time on
On the small.
No, also model turbulence, right?
Yeah.
So would this be something that an unsteady trans model or some sort of really physical order reduction capture your opinion?
This type of what aspect of it?
Well, it's obviously a very turbulent flow if you look at it this way.
Yeah.
But that kind of spectrum tells me that maybe this is a modulation that we get to the model.
Yeah. Yeah, it's possible from the physics angle. Yeah, it's possible, but again, so
Do we agree that if this was a small scale, say the interaction of turbulent and combustion on a small scale, that you missed in your use of the model, you won't go, right?
Actually, that is the position I had when I started the project.
Okay.
But slowly I've learned to like respect this because, so think about
There was
it.
a
Right?
lack of respect.
I had a lot of lack of respect. You know, literally, I wrote the proposal and told the program manager during the interaction period that I don't think there's any chance this will work. But I respect this more. But think about it, right? So let's say that you have only one basis mode, and that basis mode is the snapshot of the flow at that point. Then it's captured all of the information, right? So you're not throwing away anything as long as you adapt. So technically speaking, if you adapt at theoretically speaking, you adapt at every time step, and that adaptation is perfect, then you need only one basis, which is the flow field snapshot. So you're not missing the details. So here, so that is what's happening. So here I have only 5 modes of a 500K degree of freedom system. And if I use a static basis, what we said was correct. I've done, even in the very first snapshot, very first time step, I would have missed the small scale, and there is no way I can recover it. But here, you're actually going after that, okay? But you could argue that after some point you may miss it. But because we have the equations and we are looking at the residual of the equations to guide us to adapt, that may also be possible. But if it is one rare event that matters to the entire physics and you miss that, then you're probably done. But in this case, small events happen maybe periodically. So when you depart from some type of low resolution, you can get it back. But this is more like a delete. But yeah, I can maybe design a problem where there are these multiple small scale things that happen, rare events, and those dictate what happens at a large scale and see how they do it. That's possible, yeah. But like I said, I mean, this is actually capturing the small scale. So it's not removing the small scale information. In fact, maybe I went through that very quickly, but when I spoke about this discussion here, so here QR is the large scale, and this QR perpendicular is the small scale. Yeah, and that's what you miss if you keep the basis the same. But if you keep adapting, effectively you're recovering that. So every time step, you're actually rotating the manifold to like do a best fit. So you're not throwing away what you missed.
But taking random snapshots to account for this
No, it's a good idea.
mistake in the process.
Yeah, that could also work. Anything else? So how did I do one? Yeah.
So instead of doing it, let's say, for two-order model and then just order model, you compare with things like AES, for example, or possible?
I mean, the DNS to be the truth and then doing it with LES and building snapshots. Well, I don't.
No, what would have been if you were, so you do your
Yeah.
and then you have the DNS, but then to do an AES of the same thing to see whether you are outperforming or doing more.
Yeah. Yeah. And
have you done something like that?
actually, in the conclusions of Nick's thesis, that's what we wrote. We actually don't think of this as a reduced order model. We think of it as a replacement for a solver. You can think of your solver operating in DNS mode, and then you switch to this. So this would be like an LES, right? You could do in situ order reduction. So it's not really a reduced order model more. It's more like a solver replacement. So yeah, certainly. So in the future, we are trying to, like, again, maybe this is going slightly off topic, but we're saying when we build scientific solvers in the future, having the machinery to do these kind of things on the fly would help in many ways, including solver acceleration, coarse graining, some kind of parametry explorations, even if you're doing filtering and you want to do some estimates. So for all of these things, it can be useful. So it's not just a reduced order model, it could be a coarse graining or adaptive coarse graining in that sense. So yeah, it's possible. Yeah. Good.
You're using ramps everywhere.
Yeah.
Could you produce
No, because here the best we can do is the full order model that we start with, right? Where we built our bases on and where we're correcting the bases.
much simpler?
Mm-hmm.
All you care about are those two terms.
Yeah.
Not the schedule.
Yeah, it is possible that it might find some kind of reduced viscosity, but still here everything is see, I'm still like projecting the governing equations onto the basis, right? So I can only do as well as the governing equations. There is no way I can do better.
No, say, let's forget that.
Yeah.
All you care about are those two terms.
Yeah.
Could you use a much simpler model?
If it is possible for that simpler model to do it, then yeah, for sure, yeah.
Yeah, so you make the question sharper and then you return the table tomorrow.
Yeah.
If you go back to these two terms.
Yeah. Okay. If that was the only thing that mattered, can we do it with a simpler model?
No, I'll tell you
Yeah.
Yeah.
No.
Okay.
That's why we paid for it.
Did you? I will not ask. I will not.
He's paying for dinner. I mean, I think he's personally paying for dinner. No, please. This is the only reason we are here for good discussion.
I appreciate this discussion very much. I mean,
yeah.
This line is a linear line, right? Down there, the temperature is a linear.
Sure.
So it's easy.
Well, it's in log.
Yeah, fine.
Oh, it's actually not log. This one is in log.
They're wide log,
yeah.
So it's, I mean, visually, it looks, again, I'm being provocative.
No, you should be.
And I'm just exaggerating this illustration. It looks simple.
Yeah.
That's the problem. If you have a separated flow, or if you look at you have vorticity flow, vorticity maxima, statistics, things like that, what would it look like?
Yeah, we could try it. We can look at it. Yeah, so I think one of the ideas here was train a minimal flow unit and stitch them all together, do a channel flow, right? So
I appreciate the complexity very much.
Yeah, sure.
I'm just trying to...
No, I mean, we've thought about those things as well.
Yeah.
I mean, we've been busy getting these things to work and telling it.
Do you have error bars in the simulations also? How do these things change? You make about hyperparameters?
No, we don't, but it's certainly in the future. We can actually do error estimates. The advantage of having this linear machinery is at least certain aspects of what we're doing, we can have error bars, but that will require running ensembles of simulations. But I think your question is nice. So these are still large-scale phenomena, and even connecting to what Gianluca was asking. If we take turbulence, let's take wall turbulence, and then let's go after the statistics, PDFs, and see if we're able to get that. That would be nice. I mean, open for collaborations anytime. I mean, now we really want these kind of techniques to be applied to many different problems and raise interesting questions, right? Gianluca's question, I said yes, theoretically it's possible, but yeah, we'll have to see. But that will be a good challenge. But Roger, I think I didn't quite get your question, but so whatever I'm showing here, it's all still based on solving a set of equations, right? And that set of equations, if that is unsteady ranks, it can only do what the unsteady ranks can do. It cannot exceed that capacity. So I don't know if an unsteady ranks will get the mixing right to do this, right? So I can.
So that's my question. Do you need the full mixing to get predict?
I wouldn't. Oh, in this case, I would need the full mixing to predict. Yeah, URANs will not do it. Right? So I cannot exceed the capability of the full order model equation. So I showed the two branches. Actually, I mean, half of my work is in the other branch, which is taking a reduced fidelity model like URANs and then embedding learning operators within it and improving accuracy of the model. So I didn't talk about that today, but that's a pretty large activity for us. Okay, it was great discussion. I had a few points for us to mull over in the panel discussions. I didn't show it, but yeah, I think it's going to be exciting. Thank you very much.
Thank you.
Yeah.